For decades, astronomers have depended on powerful space telescopes like Hubble, James Webb, and Chandra to unveil the universe with a level of sharpness and depth that no instrument on Earth could ever match. Yet something truly remarkable has just taken place. A groundbreaking telescope that remains firmly anchored to the ground, still operating beneath our planet's thick atmosphere, has produced images of such immense scale, breathtaking detail, and profound cosmic depth that scientists around the world have paused in collective astonishment. The Vera C. Rubin Observatory has finally opened its eyes to the night sky for the very first time. And what it revealed during those initial observations is not simply beautiful or impressive, it is genuinely unsettling in its vastness and complexity. It offers a glimpse into a sky so densely packed with activity, so dynamic and so overflowing with cosmic drama, that it threatens to fundamentally rewrite how we understand and map the universe itself. A camera the size of a small automobile that records an astonishing 3.2 billion pixels in every single frame. A single exposure wide enough to comfortably contain the area of 40 full moons. A data stream so enormous that it will require entire scientific careers to fully interpret and analyze. And yet, even these very first images already contain secrets that challenge long-held assumptions. Merging galaxies caught in the midst of dramatic collisions, newborn stars emerging from glowing clouds of gas and dust, tens of thousands of ancient star clusters scattered across the sky, and more asteroids detected in just 10 hours than the rest of humanity had discovered over many weeks of previous observations. This marks the moment that astronomers have been anticipating for years. A revolutionary machine powerful enough to monitor the sky in constant motion, to catch fleeting cosmic events the instant they unfold, and to reveal hidden structures and phenomena we did not even know existed. Tonight, we dive deep into what the Vera C. Rubin Observatory has just shown us, and why its inaugural images have sent shockwaves throughout the global scientific community. Long before the first photons ever reached its sensors, the Rubin Observatory had already achieved legendary status in astronomical circles. Perched high atop Cerro Pachon in Chile, one of the driest, clearest, and darkest observing locations on the entire planet, it was engineered not merely to capture photographs, but to conduct the most comprehensive and ambitious survey of the universe ever attempted by humanity. At its core sits the Simony Survey Telescope, featuring a sophisticated 3-mirror optical design that delivers exceptional sharpness and an extraordinarily wide field of view, far surpassing what conventional 2-mirror systems can achieve. The primary mirror alone stretches 8.4 meters across, providing immense light-gathering power. Yet, what truly distinguishes Rubin from every previous observatory is the seamless integration of this advanced optical system with the largest digital camera ever constructed for astronomical purposes. This remarkable camera weighs nearly 3 tons, measures more than 3 meters in length, and captures light across ultraviolet, visible, and near-infrared wavelengths with unmatched sensitivity and precision. What sets Rubin apart even more dramatically is its sheer operational ambition and scale. Each individual image spans a full 10 square degrees of sky. In one single snapshot, it records an area that would require the Hubble Space Telescope thousands of separate exposures to assemble. As it systematically scans the southern sky every few nights, Rubin does not simply create static photographs of distant objects. Instead, it constructs an evolving, living time-lapse record of the entire cosmos, revealing the subtle flickers, sudden outbursts, dramatic collisions, and gradual transformations occurring across vast cosmic distances. This is not an instrument built to study isolated celestial targets in isolation. It exists to observe everything simultaneously, creating the most complete and dynamic map of the universe that humanity has ever possessed. When the observatory captured its very first scientific images in June 2025, researchers around the world anticipated impressive results based on years of careful planning and engineering. They were not prepared, however, for the sheer overwhelming depth, richness, and complexity of what Rubin actually delivered. After slightly more than 10 hours of initial test observations, the telescope produced a breathtaking mosaic that the astronomical community quickly nicknamed the Cosmic Treasure Chest. This stunning 25 square degree portrait focused on the southern portion of the Virgo cluster, the nearest major galaxy cluster to our own Milky Way. Assembled from 1,185 individual exposures, the image contains millions upon millions of stars and galaxies spread across the frame. Spiral galaxies unfurl their graceful arms across the void in intricate patterns. Pairs of galaxies merge in dramatic cosmic dances resembling swirling smoke and colliding stellar systems. Vast filaments of matter link distant clusters in intricate web-like structures that trace the large-scale architecture of the universe. In the background, faint reddish smudges hint at countless additional galaxies, each potentially home to billions of planets and untold numbers of stars. And this overwhelming abundance of cosmic detail represents merely 0.05% of what Rubin is ultimately expected to detect and catalog during its full decade-long survey. The observatory is projected to reveal around 20 billion galaxies over the course of its mission. This first mosaic serves as a tantalizing preview, the opening trailer for an epic cosmic documentary that will unfold across 10 years of continuous systematic observation. As astronomers examined the mosaic more closely in the days following its release, they discovered far more than mere visual beauty. If this initial mosaic showcased Rubin's extraordinary imaging power and technical capabilities, its subsequent release proved something even more profound and unexpected. A ground-based observatory could rival, and in certain important respects surpass, the depth and contextual breadth traditionally associated with space telescopes. The Rubin team unveiled a wide-field mosaic of the famous Lagoon Nebula, a vibrant and active star-forming region located approximately 5,100 light-years away in the direction of the constellation Sagittarius. Traditionally, scientific views of the Lagoon Nebula have come through tightly framed, highly zoomed-in images captured by instruments like Hubble. Rubin offered something entirely different and far more comprehensive. A sweeping panoramic vista where the nebula itself, despite spanning 55 light-years across, occupies only a modest portion of the overall frame. Surrounding it stretch countless points of light representing open star clusters, such as Messier 21, the glowing Trifid Nebula, various Bok globules, and the densely packed globular cluster NGC 6544. In one unified and breathtaking view, Rubin captured celestial structures existing at vastly different distances and evolutionary stages within the same frame. Newborn stars, still embedded in their natal clouds of gas and dust, appear alongside ancient globular clusters located thousands of light-years farther away in the galactic halo. This remarkable capability stems directly from Rubin's unparalleled field of view combined with its exceptional optical precision. While Hubble might capture an area equivalent to roughly 1% of the Moon's surface in a single frame, Rubin can comfortably encompass the area of 40 full moons simultaneously. And despite this immense coverage, the level of detail remains razor sharp from the very center all the way to the edges of each exposure. For the first time in history, we see the Lagoon Nebula not as an isolated and disconnected phenomenon, but as an integrated element within a much larger cosmic environment. It becomes a bustling neighborhood filled with ongoing stellar birth, dramatic death, chaotic interactions, and continuous transformation on multiple scales. Rubin was never intended simply to produce beautiful astronomical pictures for public appreciation. It was engineered from the ground up to fundamentally transform the entire practice of modern astronomy. And even during these very preliminary test phases, it is already fulfilling that ambitious promise in spectacular fashion. In just 10 hours of initial operation, the observatory identified more than 2,000 previously unknown asteroids, including several near-Earth objects that pose potential future monitoring needs. To fully appreciate the significance of this achievement, consider that the combined efforts of observatories worldwide typically discover around 20,000 asteroids per year. Rubin is positioned to find millions during its early years alone. It may well become the single most powerful tool humanity has ever created for detecting and tracking potential impact threats long before they approach our planet. And asteroid hunting represents merely one of 4 primary scientific missions that Rubin was designed to accomplish during its decade-long survey. Rubin will also conduct an unprecedented search for clues about the mysterious nature of dark matter and dark energy by meticulously mapping how galaxies cluster and move across billions of light-years of cosmic distance. It will serve as a vigilant monitor for transient cosmic events such as supernovae, gamma-ray bursts, and unusual stellar outbursts, catching them in the precise moment they occur thanks to its rapid scanning schedule that covers the sky every few nights. It will track ancient RR Lyrae stars, potentially discovering 100,000 of them to create unprecedented maps of the Milky Way's outer halo and faint tidal streams left behind by ancient galactic collisions. Behind all these ambitious scientific goals lies the true staggering scale of the endeavor. Rubin is expected to generate 500 petabytes of raw data by the conclusion of its 10-year survey. This represents trillions of individual measurements and billions of celestial objects, creating a decade-long time-lapse record of the universe that will require generations of scientists to fully explore, analyze, and interpret. Rubin is far more than a telescope. It is a cosmic observatory designed to rewrite the fundamental rules of astronomical discovery for the 21st century and beyond. To truly appreciate why the Vera C. Rubin Observatory's first images have generated such widespread excitement and even astonishment among astronomers worldwide, one must first understand the long-standing and formidable challenges of conducting high-precision observations from the surface of our planet. ground-based telescopes must constantly contend with the distorting effects of Earth's atmosphere, including turbulence that blurs incoming starlight, temperature fluctuations that affect optical performance, humidity that can scatter light, dust particles that reduce clarity, and subtle refractive distortions that are invisible to the naked eye but devastating to image quality. These atmospheric factors explain why flagship space observatories like Hubble and James Webb were placed in orbit, escaping Earth's turbulent atmospheric cage entirely to achieve their legendary sharpness and depth. Yet Rubin defies this conventional wisdom in spectacular fashion. Constructed atop the exceptional observing site of Cerro Pachon in Chile's remote Atacama Desert, it benefits from some of the clearest, driest, and most stable atmospheric conditions available anywhere on the surface of our planet. Rainfall is virtually non-existent for long stretches, clouds are rare visitors, and artificial light pollution is almost completely absent across the vast surrounding landscape. The Atacama region already hosts many of the world's premier astronomical facilities for precisely these reasons, and Rubin takes full advantage of this pristine environment through its innovative three-mirror optical design, massive digital camera array, and fully automated nightly survey strategy. Together, these elements allow it to overcome many of the traditional limitations that have historically constrained other ground-based observatories. The outcome is images possessing both extraordinary depth of field and unmatched contextual breadth, rivaling and occasionally surpassing the quality traditionally associated with instruments operating from space. For a telescope firmly anchored beneath Earth's atmosphere to accomplish this represents not merely an incremental improvement, but a genuine revolution in the field of observational astronomy. It signals the dawn of a new era where ground-based and space-based instruments can function as true complementary partners rather than competitors in the shared quest to unlock the universe's deepest mysteries. One of Rubin's most remarkable achievements lies not solely in its impressive hardware, but in the sophisticated digital infrastructure required to handle and process its truly enormous data output. The observatory is projected to generate approximately 20 terabytes of raw information every single night, a volume so vast that it would overwhelm conventional astronomical data management systems. To manage this relentless flow, engineers established a dedicated 100 gigabit per second fiber optic connection that transmits data directly from the remote Chilean mountaintop to a major processing center in the United States. From there, the information enters an advanced real-time processing pipeline that calibrates images, aligns multiple exposures, corrects for atmospheric distortions, identifies moving objects, flags transient events, and continuously updates an ever-expanding digital map of the entire sky. All of this sophisticated processing occurs automatically before human researchers even begin their detailed scientific analysis. What Rubin is constructing is far more than a simple collection of astronomical photographs. It is creating a living, dynamic, and continuously evolving digital representation of the universe that refreshes itself every few nights with fresh observations. Imagine replacing traditional static star charts and limited photographic plates with an evolving, responsive model of the cosmos capable of revealing changes faster than astronomers can manually respond to them. A supernova erupts in a distant galaxy. Rubin detects it almost immediately and alerts the community. An interstellar object streaks through the outer reaches of our solar system. Rubin captures its trajectory and characteristics in real time. A distant star exhibits unusual variability in its brightness. Rubin records the pattern and adds it to the growing catalog. The observatory functions not only as a passive observer, but as an active monitor, cataloger, and early warning system for the universe. It serves as humanity's continuous surveillance system for the cosmos, identifying shifts and broadcasting alerts to scientists globally within minutes of detection. Prior to Rubin, many brief and unpredictable cosmic phenomena were frequently missed entirely, appearing only within the narrow fields of view of scheduled telescopes or falling between observation windows. Rubin's persistent and systematic monitoring changes this equation entirely. It constructs a comprehensive cosmic heartbeat, capturing the universe not as frozen moments in time, but as a vibrant, ever-changing, and endlessly dynamic entity. Beyond its groundbreaking contributions to galaxy surveys and transient event detection, Rubin's early observations of RR Lyrae stars point toward another potentially transformative scientific capability. These ancient pulsating variable stars serve as highly reliable standard candles for measuring cosmic distances with remarkable precision. Rubin has already identified dozens of them in its initial test images, with scientific projections suggesting it could eventually catalog up to 100,000 such stars across its full survey. Many RR Lyrae variables reside in the distant galactic halo or within faint tidal streams left behind by ancient galactic collisions and mergers. These regions have historically proven extremely difficult to map in detail due to the star's relative faintness and sparse distribution across the sky. Rubin's powerful combination of wide field coverage, exceptional sensitivity, and repeated scanning cycles transforms this long-standing challenge into routine science. The observatory effectively becomes a cosmic cartographer of unprecedented power, revealing the hidden architecture of our galaxy's outer reaches and uncovering preserved evidence of ancient mergers and interactions written in the faint light of its most distant stars. By the conclusion of its 10-year mission, Rubin's accumulated data will likely transform our fundamental understanding of the Milky Way's true three-dimensional structure and evolutionary history. What we currently perceive as a relatively straightforward spiral galaxy may ultimately reveal a far more complex and dramatic past, preserved in the subtle motions and distributions of its outermost stellar populations. This detailed mapping effort will connect our local cosmic neighborhood to the broader universe in ways never before possible, providing new insights into how galaxies like our own form, evolve, and interact over cosmic timescales. While many astronomical telescopes rely on conventional CCD detectors for imaging, Rubin employs something far more ambitious and technically sophisticated. Its 3.2 billion pixel camera represents the largest astronomical imaging device ever constructed. This is no ordinary sensor array. It functions as a precision, scientific instrument carefully designed to capture light across ultraviolet, visible, and near-infrared wavelengths with extraordinary sensitivity and accuracy. The camera assembly itself stretches nearly 3 meters in length and contains 189 individual sensors, each meticulously calibrated and aligned to ensure seamless integration across its enormous field of view. The true optical excellence of the system comes from its trio of massive fused silica lenses, including the largest lens ever manufactured specifically for astronomical purposes. These carefully engineered optical elements work in perfect harmony to minimize distortion and maintain exceptional sharpness from the very center of each frame all the way to the distant edges. A sophisticated robotic filter-changing system allows rapid transitions between different wavelength bands, enabling flexible and responsive observation strategies tailored to specific scientific questions. The resulting data products are not traditional photographs, but rich multidimensional information sets containing chemical signatures, temperature indicators, spatial relationships, and motion vectors that remain invisible to the human eye. Rubin does not simply image the sky in the conventional sense. It extracts the underlying physical properties and dynamic behavior of celestial objects across vast areas of the cosmos with unprecedented efficiency and detail. Comparing Rubin directly to the Hubble Space Telescope highlights their beautifully complementary strengths and different design philosophies. Hubble excels at ultra-detailed studies of individual objects within extremely tiny fields of view. Rubin was purpose-built for scale, context, and dynamic monitoring. One Rubin image can comfortably encompass an area equivalent to 40 full moons while maintaining remarkable sharpness and detail from center to edge. This allows astronomers to understand not just isolated cosmic features in exquisite detail, but also their larger relationships within surrounding structures and environments. Hubble reveals the intricate internal anatomy of a star-forming region like the Lagoon Nebula. Rubin shows how that same region fits into the broader galactic ecosystem, surrounded by clusters, filaments, and other structures across immense distances. Together, these observatories provide both microscopic precision and panoramic perspective, creating a more complete and nuanced picture of the universe than either could achieve in isolation. Rubin's first light images already demonstrate this powerful synergy in action. The observatory's ability to capture both fine structural detail and immense contextual information simultaneously within the same frame represents a genuine breakthrough in astronomical imaging capabilities. For the first time, we can study cosmic phenomena across vastly different physical scales and evolutionary stages within a single unified view. This capability will undoubtedly accelerate discoveries across multiple fields, ranging from solar system science to extragalactic astronomy and cosmology. The era of primarily static astronomy based on isolated snapshots is gradually ending. Rubin heralds the beginning of a new dynamic, time-domain astronomy, conducted on an unprecedented scale and with unmatched temporal resolution. The true revolutionary aspect of the Vera C. Rubin Observatory lies in its capacity to transform enormous quantities of raw observational data into actionable scientific insight at remarkable speed. Its advanced automated pipelines process information in near real time, identifying new objects, flagging unusual activity, and continuously updating vast astronomical catalogs with fresh discoveries. This fundamental shift moves astronomy from occasional discrete snapshots toward continuous, systematic monitoring of the entire sky. Events that once required extraordinary luck or precise timing to observe can now be caught systematically as they occur across the cosmos. Supernovae, variable stars, asteroid movements, and other transient phenomena become integral parts of an ongoing cosmic record rather than rare and isolated discoveries. This change in fundamental approach will likely lead to numerous breakthroughs across multiple branches of astrophysics throughout the coming decade and beyond. Rubin's impact extends well beyond the realm of professional science alone. By making large portions of its rich data publicly accessible through user-friendly online platforms and tools, it democratizes astronomy in unprecedented ways. Anyone with a basic internet connection can now explore the cosmos using the same high-quality datasets previously available, only to specialists with access to major research facilities. This openness invites citizen scientists, students, educators, and astronomy enthusiasts from around the world to participate directly in the process of discovery. The potential for unexpected and valuable findings from engaged members of the public is enormous and genuinely exciting. Rubin is not simply another professional observatory. It is rapidly becoming a shared global resource that allows all of humanity to participate in the ongoing exploration and understanding of our universe. As the Vera C. Rubin Observatory continues its systematic survey over the coming years, the pace of new discoveries will only continue to accelerate. Each night of operation adds fresh layers of information to our ever-growing cosmic map. Each completed scan reveals previously hidden structures, unexpected phenomena, and new questions about the nature of the universe. The observatory stands as a powerful testament to human ingenuity, scientific ambition, and collective curiosity. It is a machine specifically designed to answer some of humanity's most fundamental questions about the cosmos, while simultaneously raising entirely new ones in the process. Its first images have already exceeded the expectations of even the most optimistic astronomers. The coming decade promises a steady stream of revelations that will reshape our understanding of the universe and our place within it in profound ways. The Vera C. Rubin Observatory has opened a vibrant new chapter in humanity's long journey of cosmic exploration, one written in the collective light collected from billions of celestial objects scattered across vast distances and deep cosmic time. We are only beginning to read this grand story, but its opening pages have already captured the imagination of the world.